Okay, let's dive right into this. Welcome to the Explainer. Today, we're unlocking the hidden mathematical framework that literally governs the world around us. Yep, we're talking about arithmetic progressions. Now, I know, the second someone drops the phrase math formulas, it's super tempting to just zone out. But stick with me here. We're not just staring at numbers on a page today. We're going to decode the actual matrix of reality, from how massive buildings stay standing to exactly how your savings account grows.
Here's our quick roadmap for today. We'll start with patterns in real life, unpack exactly what arithmetic progressions are, figure out how to find that elusive nth term, sum it all up, and finally put these formulas to work in the real world. So let's kick things off with part one, spotting these patterns in real life and actually visualizing the math.
And there's a perfect visual for exactly what I mean here. When you see a stunning structural sequence like endless brick arches receding down a hallway, your brain instantly recognizes the rhythm, right? That precise repeating spacing. Well, that is definitely not an accident. It's a meticulously calculated mathematical sequence brought to life right there in the architecture.
We actually see similar continuous sequences everywhere. You'll spot them in human design, like intricate spiral staircases, and all over nature, too. Think about a biological sequence. A single cell dividing into 2, then 4, then 8, and then 16. The universe absolutely loves a predictable pattern. But to truly understand how these patterns work, we need a very specific mathematical key. Which brings us to part two. Let's unpack arithmetic progressions and get into the actual mechanics of the math. Okay, here's the formal definition we'll be working with. An arithmetic progression, which we'll just call an AP to save some breath, is a sequence where successive terms differ by a constant value. Now, I really want you to mentally highlight that phrase, constant value. We call this the common difference, and honestly, it's the absolute secret sauce to this entire concept. Whether you're adding a positive number, a negative number, or even a weird fraction, as long as that change is exactly the same every single time you jump to the next term, you've got yourself an AP. So the crucial point here is clearing up a super common mix-up, sequence versus series. A sequence is literally just the list of numbers following our rule. For example, 1, 5, 9, 13. See the rule there? We're adding exactly 4 to each term to get to the next one. That constant jump of 4 makes it a sequence. A series, on the flip side, is what happens when you take that exact same list and add all the numbers together. You're literally just swapping out the commas for plus signs. So 1 plus 5 plus 9 plus 13. Makes sense. Now, to totally master this, we're going to need a toolkit. But please don't look at these as boring algebraic letters. Think of them as your cheat codes. A is your starting line, the very first term in your sequence. D is the engine, that common difference that's driving the whole sequence forward. N is your target position, basically the number of terms you're dealing with. And Tn, which you might sometimes see written as An, well, that's the actual value of the term sitting at that specific end position.
All right, moving to part 3, finding the nth term. I like to think of this as mathematical time travel.
Let's actually test this out. Say we have this sequence, 3, 7, 11, 15, and we need to find the 10th term. Sure, you could manually count this out on your fingers, but what if the question asked for the 1000th term? Yeah, that manual counting strategy breaks down immediately. Nobody has time for that. We need a way faster method. Enter our first cheat code formula. Tn equals A plus, inside parentheses, n minus 1, all multiplied by d. This single formula is your ultimate shortcut. It literally lets you leapfrog over all those annoying intermediate numbers and land precisely on any position in the sequence you want. Let's see this thing in action. Let's move to it and see exactly how this builds. Step 1, we grab A, our starting number, which is 3. Step 2, we find D. Just subtract the first term from the second. So 7 minus 3, which gives us our constant common difference of 4. Step 3, plug it all into the formula. T10 equals 3 plus 10 minus 1 times 4. Step 4, we solve. 10 minus 1 is 9, 9 times 4 is 36. Add that to our starting 3 and boom, exactly 39. Smooth, fast, and perfectly accurate. Okay, section 4, summing it all up and finding the total value. Imagine being hit with this incredibly daunting question on a test. Find the total sum of the first 1,000 terms of the sequence 1, 2, 3, 4, and so on. If you try to do this manually on a calculator, you're going to be there all day, your thumbs will literally go numb, and you'll almost certainly make a typo somewhere. We desperately need a tool that can do some heavy lifting here. Well, here is your heavy lifter, the summation formula.
Summation, which just means the sum of terms up to position n, equals n divided by 2, multiplied by the entire quantity of 2 times a, plus n minus 1 times d. Okay, I know, it sounds like a lot of mathematical alphabet soup, but trust me, it is incredibly powerful. Let's plug in that 1,000-term problem and see.
Let's execute this step by step. Step 1. Our first term, a, is 1. And since we're just counting up by ones, our difference, d, is also exactly 1. Step 2. Our n, the total number of terms we want to sum up, is 1,000. Step 3. Plug it in. 1,000 divided by 2 is 500. Inside the brackets, we have 2 times 1, which is 2, plus 1,000 minus 1 times 1, which is just 999. So the math is really just 500 multiplied by 1,001. And step 4, in mere seconds, without adding a single 1,000 individual numbers, we find our exact sum is 500,500. No numb thumbs required.
Now, as a quick aside, there is actually a second, slightly sleeker summation formula. Sn equals n divided by 2, multiplied by a1 plus an. This works beautifully and honestly saves you even more time. But there's a catch. You can only use it when you already know both the very first term and the very last term of your sequence. If you have those, definitely use this. All right, final stretch, part 5. Putting these formulas to work with real-life applications. Now, what's really interesting here is seeing how these abstract letters become completely practical in the real world. In finance, arithmetic progressions actually govern your budgeting and savings, like scaling up your investments by a set amount, say 100 rupees extra each month. In science, physicists use these exact same formulas to model uniform motion. Think of tracking a car that's increasing its speed by exactly 10 kilometers per hour every single minute. Or urban planning. Civil engineers use APs to lay out infrastructure, making sure streetlights are placed exactly every 20 meters to completely optimize lighting and safety. And here's one more example that impacts pretty much all of us: event management. Have you ever bought concert or theater tickets? The way those pricing tiers work, where the ticket price jumps by a fixed amount, say 50 rupees for every row you move closer to the stage, that is quite literally just an arithmetic progression in disguise. The event organizers are straight up using that TN formula we just learned to generate their seating map prices. Mind-blowing, right? So we've officially broken the code. You now know that behind the repetitive structures of our physical and financial world lies this super simple, highly predictable rule of common differences. Math isn't just a bunch of arbitrary rules teachers make you memorize, it's the hidden architecture of reality itself. So I'm going to leave you with this thought. Take your new cheat codes, look around whatever room you're sitting in right now. Can you spot an arithmetic progression hidden in plain sight? Think about it and keep exploring.